Welcome to all. In this lecture, you will learn what is a linear Diophantine equation and how to solve it. A Diophantine equation is a polynomial equation with integer coefficients for which integral solutions are required. For example, consider the equation 2x plus 3y equal to 4 and x square plus y square equal to 4 where x and y are integers. Note that these two equations are polynomial equation in two variables x and y with integer coefficients, and here we restrict x and y as integer values. It means we are interested in integer solutions of this equation. So, these two equations are Diophantine equation. Next we define linear Diophantine equations, in short we call LDE. A linear Diophantine equation in two variables x and y is a Diophantine equations of the form ax plus by equal to c. In other words, any equation of the form ax plus by equal to c where a, b, c, x and y are integers is called a linear Diophantine equations. In the example given above, 2x plus 3y equal to 4 is a linear Diophantine equations, but x square plus y square equal to 4 is not a linear Diophantine equation. Next we generalize the definition to n variables. A linear Diophantine equation in n variable x1, x2 up to xn is a Diophantine equation of the form a1 x1 plus a2 x2 up to an xn equal to b. Next, now we try to solve a LDE. Before this, we arise a question whether all the LDE has solution. To see this, we consider the following LDE: 2x plus 4y equal to 5. Note that if x is an integer, then 2x is a multiplication of an even integer and an integer. So, 2x is an even integer. Similarly, 4y is an even integer. We know sum of two even integer is an even integer. Thus, 2x plus 4y is always even, whereas the right hand side of the equation is 5, which is odd. An even integer, an even number cannot be equal to an odd number. So, there is no x and y satisfying the LDE 2x plus 4y equal to 5. So, the LDE has no solution. From this example, we observe that every LDE need not have a solution. So, next we arise a question: under what condition a LDE has solution? Indian mathematician Aryabhatta answered this question for two variables LDE, which is given in the next theorem. This theorem establishes a necessary and sufficient condition for the LDE ax plus by equal to c to be solvable. Solvable means integer solution exists for the LDE. So, theorem 1, the LDE ax plus by equal to c is solvable if and only if d divides c, where d equal to GCD of AB, if x naught y naught is a particular solution of the LDE, then all its solutions are given by x equal to x naught plus b by d into t and y equal to y naught minus a by d into t, where t is an arbitrary integer. So, now we prove the theorem. The proof consists of 4 parts. So, the first part is if the LDE is solvable, then d divides c. Next part is converse part. If d divides c, then the LDE is solvable. Next we prove x equal to x naught plus b by d into t and y equal to y naught minus a by d into t is a solution of the LDE. The final part is every solution of the LDE is of the form x equal to x naught plus b by d into t and y equal to y naught minus a by d into t, where t is an arbitrary integer. So, now we prove the first part. To prove the first part, we assume the LD is solvable. We are going to prove D divides C. So, LD is solvable means the LD has solutions. We take the solutions as alpha and beta. So, alpha and beta satisfy the LDE. Therefore, we have alpha A plus beta B equal to C. Since D is GCD of AB, so GCD means the greatest common divisor of A and B. So, D divides A and D divides B. So, D divides A and D divides B implies D divides linear combination of A and B. This is my theorem. So, D divides A alpha plus B beta. So, alpha A plus beta B value is C. So, obviously this implies D divides C. So, now we proved the first part. Now, come to the second part. So, in this part we assume D divides C. We are going to prove LD is solvable. So, first assume the D divides C. So, D divides C implies C is a multiple of D. So, C equal to D into E for some integer E. Since D is GCD of E, so by theorem GCD of AB can be written as a linear combination of A and B. So, D equal to RA plus S in RA plus SB for some integers R and S. So, now we multiply both sides by E. So, we get RAE plus SBE equal to DE. We know DE equal to C. Thus, we have A into RE plus B into SE equal to C. Thus, RE and SE are solution of this equation. So, this LD AX plus BY equal to C has a solution. So, this LD is solvable. Next, we prove x equal to x naught plus b by d into t and y equal to y naught minus a by d into t is a solution. To prove this, we simply substitute x and y value in the given equation and we verify whether the x and y satisfy the equation or not. So, substitute the x and y value in the equation. So, ax plus by equal to a into x naught plus b by d into t plus b into y naught minus a by d into t. We multiply a and b and group the terms. So, we get ax naught plus by naught plus abt by d minus abt by d. So, abt by d minus abt by d will be cancelled. So, we get ax naught plus by naught ax naught by naught equal to C. Since x naught and y naught are particular solutions of the equation, so x naught and x naught and y naught satisfy the equation. So, we get ax naught plus by naught equal to C. Thus, x equal to x naught plus b by d into t and y equal to y naught minus b a by d into t satisfy the equation. So, these are solution of the equation. Now, we prove the last part. So, in this part we prove every solutions is of the form, every solution of the LD is of the form x equal to x naught plus b by d into t and y equal to y naught minus a by d into t. Since x naught y naught is a particular solution and in this part we assumed x dash and y dash are solution of the LDE. So, x naught y naught and x dash y dash satisfy the LDE ax plus by equal to C. So, we get ax naught plus by naught equal to C and ax dash plus by dash equal to C. From these two equations, we get ax naught plus by naught equal to ax dash plus by dash. So, from this equation, we get a into x dash minus x naught equal to b into y naught minus y dash. Now, divide the equation by d both sides. So, we get a by d into x dash minus x naught equal to b by d into y naught minus y dash. So, here we observe that a by d into x dash minus x naught is a multiplication of b by d. So, b by d divides a by d into x dash minus x naught. Since d equal to d is GCD of AB. So, by theorem, if d is GCD of AB, then a by d and b by d are relatively prime, that is GCD of a by d and b by d is 1. So, we have a theorem, the theorem statement is given in the red color. So, this theorem states that if a and b are relatively prime and if a divide bc, then a divides c. So, from equation 2 and 3 we have a by d and b by d are relatively prime and b by d divide a by d into x dash minus x naught. So, this implies b by d divides x dash minus x naught, here c is x dash minus x naught. Hence, b by d divides x dash minus x naught means x dash minus x naught is multiple of b by d. So, we get x dash minus x naught equal to b by d into t for some integer t. So, this implies x dash equal to x naught plus b by d into t. Now, substitute equation 4 in equation 1. So, we get a into b by d into t equal to b into y naught minus y dash, b will be cancelled. So, we get a by d into t which is equal to y naught minus y dash. So, this implies y dash equal to y naught minus a by d into t. So, what do we get? First we assumed x dash and y dash are is any solution of the LDE. So, we get x dash and y dash take the form x naught plus b by d into t, y dash take the form y naught minus a by d into t. Thus, every solution of the LDE is of the form x equal to x naught plus b by d into t and y equal to y naught minus a by d into t. So, from this theorem we obtain when a LDE is solvable, it has infinitely many solutions. The reason is t is any integer. So, to each value of t we have different values of x and y value. So, this theorem states that if when a LDE is solvable, it has infinitely many solutions. Thus, either a LDE has no solutions or infinitely many solutions. It means we cannot find a LDE with exactly with a finite number of solutions. Okay. Now, come to the corollary. This corollary states that if GCD of AB equal to 1, then the LDE AX plus BY equal to C is solvable and the general solution is given by x equal to x naught plus BT, y equal to y naught minus AT, where x naught, y naught is a particular solution. This theorem is corollary is a particular part of the above theorem, here D equal to 1. So, this corollary states that if the coefficients are relatively prime, then the two variable LDE always have solution. So, next we solve one problem, some problems. So, see the example 1, determine whether the LDE 12x plus 18y equal to 30 is solvable. That is, in this problem we are going to find whether solution exists or not to this LDE. By above theorem, we have proved that the LDE is solvable if and only if the GCD of coefficients of the two variables divides the constant term C. Thus, in this problem, the the integral solution exists if GCD of 12, 18 divides the constant term 30. Here 12 and 18 are the coefficients of x and y. So, first we find the coefficients of the coefficients. So, GCD of 12 and 18 is 6. 6 divides the constant term 30. So, by the theorem the LDE has solution. Next problem, determine whether the LDE is solvable. So, here the coefficients are 2 and 3. 2 and 3 are relatively prime. So, by the corollary the LDE has solution. Next problem, example 3, determine whether the LDE 6x plus 8y equal to 25 is solvable. Here GCD of the coefficients is 2, but 2 does not divides the constant term 25. So, the LDE 6x plus 8y equal to 25 is not solvable. Example 4, solve the LDE 12x plus 8y equal to 30. In this problem, we are asking the solution of the LDE. So, first we check whether the LDE has solution or not. So, see example 1, the same equation 12x plus 8y equal to 30. By example 1, the LDE has solution. So, to find the solution, you come to theorem second part. So, in this part we prove if D divides C, we prove the LDE is solvable. Here what we did, we write the GCD D as linear combination, D equal to RA plus SB. We write the GCD of AB as linear combination of R and E, A and B. Then we multiply this equation both sides by E, where E is C by D, since C equal to DE. So, E equal to C by D. So, we multiply by E both sides, we get a particular solution. So, if we know a particular solution, from the final part we can find the general solution. So, what is the general solution? The general solution is x equal to x naught plus b by d into t, where t is an arbitrary integer, and y equal to y naught minus a by d into t. So, what we are going to first we write GCD of 12 and 18 as linear combination of 12 and 18. So, GCD of 12 and 18 is 6. We can write 6 as linear combination of 12 and 18 in this way. 6 equal to 12 into minus 1 plus 18 into 1. So, now we will write the GCD as linear combination of 12 and 18. Next, here the constant term is 6, but the constant term in LD is 30. So, if we multiply by 5 this equation, the constant term becomes 30. So, multiply 5 both sides this equation. So, what do you have? 6 into 5 30. So, 30 equal to 5 into this equation, 12 into minus 1 plus 18 into 5. So, this implies 12 into minus 5 plus 18 into 5 equal to 30. Thus, minus 5 and plus 5, x equal to minus 5, y equal to 5 satisfy the equation 12x plus 18y equal to 30. So, x equal to minus 5, y equal to 5 is a particular solution. We take the particular solution x naught equal to x naught and y naught. So, x naught equal to minus 5, y naught equal to 5 is a particular solution of the LD. Next, we find the general solution. General solution means we find all solution of the LDE. Since already we see LDE always if LDE is solvable, then it has infinite number of solutions. So, we find the infinite number of solutions, general solution. So, in the last theorem we have a formula to find a LDE. The formula is x equal to x naught plus b by d into t and y equal to y naught minus a by d into t, where t is an integer. So find what are the values of a and b. A is coefficient of x, which is 12, b is coefficient of y, which is 18, d is GCD of AB, which is equal to 6. Substitute the a, b, d values and x naught, y naught values in the formula. X equal to x naught plus b by d into t and y equal to y naught minus a by d into t. So we get x equal to minus 5 plus 3t, y equal to 5 minus 2t, where t is arbitrary integer. So which is the general solution of the LD. Okay. So next we go to theorem 3. This theorem is generalization of theorem 1. Here we speak in n variable. The LDE a1 x1 plus a2 x2 up to an xn equal to c is solvable if and only if the GCD of the coefficients a1, a2 up to an divides the constant term c. When it is solvable, it has infinitely many solutions. So example 5. Example 5, determine whether the LDE is solvable. Here GCD of the coefficients is GCD of 12, 6, 12, 15 is 3. 3 does not divide the constant term. So this LDE has no integer solution. Example 6, find the general solution of the LDE. 6x plus 8y plus 12 is equal to 10. So it is a 3 variable LDE. So first we check whether the LDE is solvable. So to verify this, to find this, we find the GCD of the coefficients. GCD of 6, 8, 12 is 2. 2 divides the constant term 10. So the LD has solution, integer solution. So first take the equation 6x plus 8y plus 12 is equal to 10. This equation can be written as 6x plus 4 into 2y plus 3 is equal to 10. I take 2y plus 3 z as u. So we get 6x plus 4 equal to 10, where u is 2y plus 3 z equal to u. Now we solve u. So we have to find out x, y, z. Okay. So now we solve equation 1. Equation 1 is a 2 variable LDE. Already we know how to solve a 2 variable LDE, which is given in example 4. What we did? First we write the GCD of the coefficient a linear combination. Then we multiply the equation by some constant, we get particular solution. Then using the formula x equal to x naught plus b by d into t, y equal to y naught minus a by d into t, we obtain the general solution. So we use the same technique here. So 6x plus 4 equal to 10. Here a is 6, b equal to 4, c equal to 10. So the GCD of AB is d, which is equal to GCD of 6 comma 4, which is equal to 2. So now we write 2 as linear combination of 6 and 4. We can write this 6 into 1 plus 4 into minus 1. So here see the first equation, the constant term is 10, but here we have 2. So multiply 5 both sides. So we get 10 equal to 6 into 5 plus 4 into minus 5. Thus x naught equal to 5 and u naught equal to minus 5 satisfy the equation 1. So which is a particular solution of equation 1. So now we know the particular solution of 1. So we can find easily the general solution of 1. So we have the formula x equal to x naught plus b by d into t, which is equal to 5 plus 4 by 2 into t. So, substitute a, b, d value, we get 5 plus 2t. Next we u equal to, here u equal to u naught minus a by d into t equal to, substitute all the values, we get minus 5 minus 3t. Okay. So, now we know one solution. The solution we need x, y, z, we have x. So, now we have to find out what is y and z value. To find out y and z, come to equation 2, 2y plus 3z equal to u. Here a equal to 2, coefficient of y, b equal to coefficient of z, which is 3, c constant term, which is equal to u. GCD of AB, GCD of AB, GCD of 2, 3, GCD of 2, 3, 1. So, now write 1 as linear combination of 2 and 3. So, how we can write? We can write 1 as 2 into minus 1 plus 3 into 1. So, now come to the equation 2. In the equation 2, the constant term is u. Here we have 1. So, multiply u both sides. So, we get 2 into minus u plus 3 into u equal to u. Therefore, y naught equal to minus u, z naught equal to u satisfy equation 2. Therefore, y naught equal to minus u and z naught equal to u is a particular solution of the equation 2. So, we know the particular solution, so we can find the general solution. So, general solution formula is given in the theorem 1. So, we use the same formula y equal to y naught plus b by d into t dash. We already used the variable t. So, here we take t dash. So, y equal to y naught plus b by d into t dash. We know y naught is minus u plus 3 by 1 into t dash. Now, substitute u value. U value is given in equation 4. So, substitute u value minus 5 minus 3t plus 3t dash, which is equal to 5 plus 3t plus 3t dash. Now, z equal to z naught minus a by d into t dash, substitute z naught a d value, we get u minus 2 by 1 into t dash. So, substitute u value, which is equal to minus 5 minus 3t minus 2 d dash, which is 6. Okay. So, now we found all the general solution, we found all the variable, x value is given in equation 3, y value is given in equation 5, z value is given 6. So, the general solution is given in equation 3, 5, 6. The general solution is x equal to 5 plus 2t, y equal to 5 plus 3t plus 3t dash, z equal to minus 5 minus 3t minus 2t dash, where t and t dash are arbitrary integer. Here we verify whether our solution is correct or not. So, we simply substitute x, y, z value in the equation 6x plus 8y plus 12z equal to 10. Here I substituted, I did some simple calculation, we get 10. So, the solution we obtained is correct. Okay, thank you.